the second lecture. So it's lecture number 2, of course number 2, something like that, on introduction to signal processing and data analysis in computer science. Just to remind you, in the first lecture, what we did is talk about representation of a set of numbers or objects with a single number. Okay, so the question was, how should I use a single number in order to minimize the representation or error with respect to a set of numbers? Then we introduced the notion of weight, of adding a weight for each and every number that we had. And then we related the notion of weight to the notion of probability. So rather than weight, we now normalize by the sum of weight, and we can treat it as some sort of probability. So we have the probability of something realizing a value which is equal to xi. And this is true if we have a finite set of numbers. What we will do in this lecture, after just finishing the previous one, is allowing something which is a little bit more sophisticated. And this something is nothing but the notion of quantization. So now I have my set of numbers, and they are ordered one after the other in a I can actually have the same 2 numbers at the same point. So here I have, for example, x7 and x8, assume that they are ordered. And here I have x9, etc., etc. And they are not uniformly distributed, but I may have a lot of them here and a few of them there. And now, rather than having a single value that would represent them, what we will deal with is with a fixed number of k numbers that can represent all of them. So bear this in mind. Let's finish the first lecture and then move into this more interesting problem that would involve 2 issues. One of them is which representative to select, and the other one is how to associate each and every number with the representative one. So if, for example, I have these 2 representatives, the question is, what should we do with x7 and x8? Should they relate to this representative or rather than that representative? Okay, so this is something that we will deal with. Before we continue, let me just remind you that it would be nice of you to open your cameras. You don't have to, but I'll be happy if you would. And another issue is that since we are not so many students, if you have any question, you can start either raising your hand or start talking. And if I would see that it is too noisy, I will control it. Otherwise, feel free to to unmute yourself, ask the question. Let's do it at the beginning as random access. I know it is very Israeli and not so common, but let's do it this way, okay? Because if something is unclear, I would be happy to answer it on the fly rather than wait until the end of the lecture. Okay, so what we will deal now so at the previous lecture, what we defined is the random variable xw, where w was the process of selecting the index and xw was the realization. So if I've selected 1, then the first x would be the one that I'm selecting, and assume that there are 2 like that. Okay? So assume that there is x and there is y. And now the question is, what would be the joint probability of both of them? So what would be the probability of selecting both w and w tilde? Okay. And apparently, we say that if these 2 variables are independent, so if my Gini, so now we have 2 black boxes, one of them is the x points and the other one are the y points. And the process of selecting the right index here would be w, and the process that selects the random variables here will be w tilde. And my Gini is selecting a point from here, and without any relation to which point is selected in the left bucket, is selecting another point from the right bucket. So if there is no relation between them, it is easy to show that the probability would be nothing but the multiplication of the probability of w and w tilde. So this would be the probability of the Gini selecting W and W tilde that can be thought of as a new index. Okay, so the combination of W and W tilde could be thought of as a new index. The product, it would be the product of the probability of selecting W and W tilde. Why do we need that? We need that because, as I will show you, I can now compute the average or the expectation of selecting X and Y. Okay, so if I have my X and my Y, the expectation of selecting both of them would be nothing but the expectation of the first times the expectation of the second. And it's very simple to prove it, because what we do is we just write the expectation equation, which is nothing but sum over all the xi and yi's over xi times yi, such that the probability of W is equal to Y and W tilde is equal to W tilde is equal to J. Now this one, since we say that the W's are unrelated, are independent, can be split into the multiplication of the probability of I and the probability of J. In multiplication, we can just move the Yj into the middle, which is what is going on here. And now, since what we have here on the right is just the J index, and what we have here is just the I index, I can take the double sum and shift it and move it to the right. So here on the right, I have multiplication over all the J's times the multiplication over all the I's. And what we have is basically that the left part is the expectation of X and the right part is the expectation of the Y. Okay, and this would be true for any linear combination of the random variable xw and x and the yw. So this was a more general case. Here I had to assume that selecting the random variables x and y is dependent. However, if they are dependent, then it appears that the expectation of any linear combination of them would be the linear combination of their expectations. So this is the last part here, the last equation, 27, applies also when the two random variables do depend on one another, which is a tricky issue. But if you just write the definition of the expectation, I mean, you write the probability of both and you sum over the x's, it would kill obviously all the y's. You sum over all the y's, it would kill all the x's, and therefore you can write it as the expectation of each of them separately. Okay, so this is averaging over the expectation operator, which is linear. Now I promised you that we will also deal with more complicated set of numbers, and specifically one set of numbers is the continuous one. So I have assumed that I have my function now as a function of t. So my psi of t would be some continuous function between 0 and 1 or 0 and whatever. This interval over t would be called delta. And here I have my numbers. And for no reason, I started and ended my function at these 2 points, this one and this one at the same level. And then I can say that my function is periodic. But for the time being, this is all I'm giving you. I'm telling you that I have a function defined on the interval delta, capital delta here. Okay, so what would be the best constant function that would represent my given function? So we can think of this given function as a set of many values, and then we know what would be the optimal. Well, each one would appear with the same probability, and take it to the limit, to the continuum limit. And in this case, we know exactly what would be the optimal representation. So assume now that I would like to represent this function by a constant function. So this would be, we'll call it psi bar, and it would be a constant function. So what would be this constant function? So for each and every value in the interval delta, my function phi bar of t would have the same value, and this would be a constant, okay? So what would be this constant? So to that end, we can either resort to the intuition that we gained before by looking at the set of numbers and representing them by a constant, or we can do the math. So let's do the math. we define an error. The error would be nothing but subtracting from psi t, from my given psi t, my estimated psi hat of t, which in this case would be nothing but subtracting from phi of t, the constant value, the constant number. So what is going on is that we'll have the definition of an error, which would be, first of all, we need to normalize by the size of my interval. So if this would be 1 and this would be 0, the size of the interval would be equal to 1. Okay, it would be basically the definition of my interval would be nothing but t at the right part, so let's call it tr minus t left. Okay, so this point would be t right or t high, and this would be t on the left. Okay, so this would be the definition of the size of the interval I'm working with. So I have to normalize by the interval just for defining it as some sort of a metric. And what I have here is defining it in an L2 sense, okay, in a mean squared error, average squared error over the interval. So I'm searching for the value phi bar such that the square of the difference between phi t and phi bar would be as small as possible. Okay, so anyone can imagine what would be my phi bar? Any hints, any ideas?
The average.
The average. So Barak, thank you. Barak is saying the average. Let's prove it. So if we prove it, what do? We write the error explicitly. So if we open the square brackets, what we get is 5 squared. Here we have minus 2 the multiplication, and here we have the constant squared. Now this is a constant. Remember, it's a constant through all t. So we can take it out of the integration. So we have what we have here is phi squared, and the integration over t is nothing but the difference of the right and left values of t, which would be nothing but the size of delta. This is how we defined it. So let's see what is going on here. Here we have the first term would be nothing but integration over the, we call it energy of the signal. The second term, again, we can take the constant out of the integration. So we have the constant times the average of the signal. Okay, this is the average, not the average. I mean, once we multiply it by 1 over delta, it would be the average of the signal. And if we continue this math, so now we push the normalization into the brackets, and what we get here is the average. The first term would be nothing but the average of the energy. The second term would be 2 phi bar times this average, and the last term would be phi squared. Now, in order to get the optimum, what we need to do is take a derivative of my error with respect to the value I'm looking for. And if we take the error, then from here what we are getting is 2 minus 2 times this guy, okay, plus 2 times phi bar. And in order to get an optimum, we equate it to 0. Now it's very easy to see what is going on here, because 2 can be cancelled. And what we get is that phi bar is equal to nothing but the average of the signal. So Barak was right. Phi optimal is nothing but the average of the signal. And it should not come as a surprise, because this is just a continuous realization of what we had before. Okay. Okay, so now let's move on. And obviously, we know that by definition, we can now plug in the phi optimal into the game. And what we get is, at the end of the day, exactly as we had before, we have integration over the square of the signal minus square the integration over the signal. So we have the average of the energy, or the second order momentum moment, from which we subtract squared of the first order moment. And obviously, by definition, exactly as before, this value is greater than 0, because we started from summing over a squared value. Okay, and again, the size of delta is nothing but integration over the interval of t. So it would be nothing but taking t on the right and t on the left, and delta would be nothing but subtracting from TR, T left. Okay, so what do we do with that? In the end, we will see that we will search for more interesting functions rather than the constant one. Okay, so this would be taking phi of t, any phi of t, between two values, between initial t0 and t1, and representing it with a constant value. Now, assume that I'm giving you a way of representing phi of t with any function that you would like. What would you do? This is a rhetorical question, so please feel free to, the answer is obvious.
Use the same function.
Exactly, thank you, Gal. So what Gal is saying is that what I would do in order to represent phi of t with any function, I would use the same function. This is not a big, this is not, for that you didn't come to this course. So now the game, next the game would be more interesting. Next, the game would be having not only phi of t, but now I will have phi 1 of t and phi 2 of t, okay, which would be another function, and phi 3 of t. And then I will have to represent all these functions with a single function. And then what you will do probably is look for the average of all these functions. But then the game would be more sophisticated, and I will tell you, look, what you have now about what you can tell about these functions is some general notion of these functions. For example, that they have some bounded energy. Okay, so assume that what I would like is to, for example, observe all functions whose second order momentum is somehow bounded. Okay, or something like the derivative, okay, with respect to t, I would like this guy to be bounded. Okay, here I'm. So it appears that for these kind of functions, so if the only thing I'm telling you is that you can bound the derivative of this function over your interval, so it is bounded by some constant, I just wrote it one without loss of generality, then it appears that there is a very special set of functions that would be optimal with respect to this representation. Anyone has any idea of, so now I'm talking about this guy. So let me try to get rid of all these guys. So this is.
Why do you bind the square and not the function itself?
Could you get closer or further away?
Why do you bind the square of the function and not the function itself? The square of the derivative or the integral?
So now I'm talking about this guy, bounding the square. This is what I'm talking about. Bounding, yeah. in the more general case, what I would talk about is bounding the gradient square of a function. So f would be my function, and now I'm bounding this guy, okay? And t could be not only one-dimensional, but 2, 3, 4, 5 dimensions. So which set of representative functions would be optimal for representing this family of, this is called Dirichlet energy, Energia Dirichlet.
Sine and cosine.
Again?
Sine or cosine.
Who said that?
Omer.
Omer. So thank you, Omer. So this would be the harmonics. This is called the Fourier. Why do you think that this is the case? I mean, how can you?
Because every function can be represented as a sum of series of weighted sinuses.
Yeah, this is true. But remember that now the game is different. The game is different because I'm telling you that you can use only 3, 4, or 5. In fact, every function can also be represented as a set of polynomials if you take a long enough sequence of polynomials. So the intuition is right. The reason is wrong. You need to think more deeply about it, and we will learn about it. It appears that if you write this equation in sort of an operator writing, then what you would do is basically say what I'm looking at is some way of looking at the square norm of this function, which is smaller than a constant, which can be written if, for example, I would look at it as in a matrix form, it would be ft, and here I'm taking the operator transpose. You don't have to know anything about it right now. We'll learn about it afterwards. And this should be, I mean, this would be my constraint. And if you look at this operator, the derivative that operates on the derivative is called the Laplacian, okay?
Mhm.
And it appears that the Laplacian can be diagonalized. And if you diagonalize the Laplacian, I'm jumping ahead, what you get is nothing but a Fourier. But we'll get there. So this is the reason of why the Fourier would be the optimal way of looking at representing smooth functions, functions that have the following property. Okay, this is, it's called the L2 norm of the gradient of the functions. So again,
Very nice.
don't, right now, just listen to the music, not to the lyrics. And at the end of the course, I do hope that you will also know the words. And when somebody would give you the Laplacian operator, you would immediately say the harmonics are the optimal way of representing smooth functions with this kind of functions. And if you care about something else, if you care, for example, about piecewise constant functions, and you would like to represent them, then there is a different set of functions that would be optimal for representing these kind of piecewise smooth functions. They are called wavelets. We'll just mention them in the course. We'll not get into the bits and bytes of them, but at least this is true for one-dimensional signals. So if you think about ECG signals or a voice or something that have a single axis, then wavelets would be the optimal way of representing this, in the sense of choosing a small number of functions in order to represent a single given functions. So in this case, in one-dimensional case, wavelets would be optimal. In the case of any dimensional space, where all we know is that the Dirichlet energy of the function is bounded, then the Fourier would be the optimal one, etc., etc. So now, after flying into 3,000 feet, let me just go back to Earth. And here are two practical homeworks that you'd need to do. The first of all is define the following function. You have the linear function, okay? The slope would be m, and the shift would be n. And what you will need to do is prove that the constant function that represent this linear function has the following error. So the error would be the size of the square, the size of the interval times square the size of the slope. And there is this factor here, 1/12, that you'd have to get, okay? So do this exercise, you'll see this 1/12 again, again, and it should be quite obvious to you that the larger the interval you choose, obviously the larger the square error would be, and the higher the gradient is, I mean, the higher the slope is, the higher the error is. So from an intuitive point of view, you should understand that what is going on here is right, but do it rigorously and compute it. Okay, then work out the MSE for x between two values low and high, where x has the weight wx, which is greater than 0, and what is the optimal theta for this case. And then consider the variable, the random variable, as some number between these two. So now we take everything to be to the continuum. So x w is equal to x with some probability. So the probability is defined in a continuous setting as selecting x between, so if this is point x, so it would be the probability of selecting x between x and x plus dx. So this would be x plus dx. So what you need to do is take everything we did for the discrete case to the continuum. So if you have a continuous probability function, what would be the error? What would be the expectation? I mean, what would be the value that I would choose in this case? And obviously, if you do it for the uniform distribution, the result should be obvious, but still work it out. So these are three homeworks that I suggest that you would do. You don't have to submit them unless unless your TAs would ask you to. Okay, so what we did until now is then how to replace and represent optimality in the sense of MSE, a number, a finite set of values, and then we also added weights, a range of values with possible weights, a random variable with given distribution, and a function over the interval. So this is what we did until now. Now what we are ready to do, okay, so now what we are ready to do is start looking at what happens when I'm giving you more than a single number to represent your numbers. So again, we are resorting back. So if you have any questions about the previous one, please raise your hands or just ask them. We are not too many students, only 24. I don't know how, because there should be more, at least there are more students registered to the course, but okay, so if you don't have any questions, then let's continue as follows. Assume that I have my set of numbers and they are ordered as before. X1 is smaller or equal to X2, etc., etc. So this is a non-decreasing given set of numbers. And obviously they can be more dense here and more sparse there. Nobody is telling me about how they are ordered on the straight line, but they are still scalar numbers. And now instead of choosing only a single representative number, now I'm changing the color, so my representative number would be not red, but rather blue. I'm choosing my representative to be 2, for example, in the simple case, or 3, or in the most general case, k. And obviously, k should be smaller than n, because if k is equal to n, what I would do is exactly like before, choose each and every representative to be the point itself, the given points themselves, okay? So somebody is giving me k, which is smaller than the number of points that I have. And now I'm being asked to find the most optimal representative, and this representative would now be called not theta, but rather theta 1, theta 2, theta k, etc., etc. So these all theta 1s are representing the first numbers from x1 to xr1, okay? All these theta 2s, I mean, the theta 2 is the same number, would represent all the numbers between x, r, and the index would be r1 plus 1 to xr2, etc., etc. Okay, okay, and I have a total of k representative numbers. So this is the game. Any ideas of how to do that? I'm quite sure that some of you should be familiar with the solution, because you probably learned it in other courses. So anyone has any idea? Let's do the following exercise.
Like the average of each group?
So
like split them to groups and then average of each group?
So who was that? Please.
Owen.
Owen. Owen Shavit?
Yes.
Okay, so what Oren said is the following. So if some oracle, some genie is splitting the x's into groups, into subgroups, then we are back in the previous joke. So somebody is giving me these splitting points, these r's, and telling me, look, the R1 should be 7, R2 should be 20, R3 should be 50, etc. So somebody has done the dirty work for me and told me where to split my x's. Then for each and every group, we know the solution. The solution would be nothing but resorting to the first lecture and selecting the average. Okay, we are fine with that. And this would be obviously a very nice solution, but we have a problem. Nobody is telling me where to set these separators. Okay, so nobody is telling me how to split my set of numbers. I have to deal with these two problems simultaneously. Splitting the sequence of numbers, the non-decreasing sequence of numbers that I have, as well as selecting the optimal representations for them. And obviously, if somebody is giving me half of the problem, I would know what the other half would be. By the way, if the other half is given to me, I mean, if somebody is giving me phi 1, and somebody is giving me phi 2, and somebody is giving me my phi k's, how would I split my numbers so that some optimality would be obtained? So now this guy is fixed, not these guys. And I now have to determine the splits. Now have to determine these guys, where to split them. So
you can find the first group by choosing the set of numbers that get the average, which you already have. and then choose the other.
So what I'm saying, what Alex is saying, is that I would choose the first group for which phi would be the average. But this is not something that I'm telling you exists. I have a set of numbers. Assume, for example, that you have your high-resolution camera that takes picture with 16 bits of color. But now your screen can display only 8 bits of color. You can't manipulate your image so that the average would be the fixed values of color that you are allowed to use. You have to do something else. So again, somebody fixed my thetas for me. So this is fixed. This is fixed. These are fixed. And now the question is where to split between the x's.
You can use Ri as the average of theta I and theta I plus 1 and split the x's between them.
Thank you, Shen. So what Shen was saying was take, so let's zoom in. Somebody is giving me theta 1 and theta 2. Shin or Sean? How should I? Sean. I was just reading in English. So what Sean was saying, take theta 1 and theta 2, for example. And now I have my numbers, which is something that is hovering here, and I don't know exactly where. But I have to split between them. So what I would do is take the midpoint between theta 1 and theta 2, okay? And relate to all points that are larger than this. So this point would be nothing but theta 1 plus theta 2 divided by 2. Am I right? This was your meaning. Now, all points that are to the right would belong to theta 2, and all points to the left would belong to theta 1. Sorry, this was not my. So all these points would belong to theta 1, and all these points would belong to theta 2. Now, is this an optimal way of splitting theta between theta 1 and theta 2? The answer is definitely yes, if we are to measure, for example, L2 error. So yes, the answer is yes. If, for example, I would take this point and relate it to theta 2, then the error that subtracting the value of that point from theta 2 would be larger than the value of subtracting that point from theta 1. And therefore, the error would increase. So indeed, choosing the midpoint between the thetas would be the optimal solution. So what I know is that given theta 1s, I know how to determine the splitting values. Given the splitting values, I know how to determine the thetas. But joining them together is something that we will try to deal with in this lecture. So let's do it. Let's try to do it painlessly, okay? And let me tell you that the problem is not trivial. The problem in the general case can be shown to be a hard problem, okay? So what we'll do is we'll have to make a lot of assumptions in order to deal with this problem. So as we did before, what we do is we so note that we map the non-increasing function of xi to the strictly increasing sequence of phi r. Obviously, if they are not strictly increasing, I mean, if I have phi 5 equals to phi 6, then I can unify them. I don't need two of them, okay? And now what we need to do is select my phi's, okay, and select my r's, and I need to do it simultaneously. Okay, so what I have here is my mean square error function with unknowns r's and phi's. Okay, so remember, my r's were the splitting points, the indices at which I'm splitting my x's. My phi's are the representative ones. So I'm splitting my domain into k intervals. In fact, it would be exactly k intervals. So I would be summing from L equals, so L would be my first interval, it would be this one. So this would be R, so this would be R1, and then I would have R2, etc., etc. So the L would be, first of all, we'll call this the 0 interval, okay? So this would be L equals 0. This would be L equal 1, etc., etc., until L equals k minus 1. And for each one, what I would do is sum over all the xi's that subtract from the, so the representative here would be theta 0, theta 1, the representative here would be theta 2, etc., etc. So I would subtract the xi's from the representatives. Okay. Now I have n. I have n ri's. I have n minus 1 theta i's. So in total, I have 2n minus 1 unknowns that I have to optimize for. How do we do that? So let's see. So again, everything we said before. If somebody is giving me the xn's and we want to determine the rj and numbers, if we fix the ri's, I mean, if we fix the points between which we split, then for each and every interval, so somebody gave me this one to be RL, and this would be RL plus 1, so this is fixed. So obviously the point that would represent all the other points would be the average of all the points. Okay, so we know that the optimal would be the average, and this is, by the way, so this is a number. So this is, for example, the 7th index, and this would be the 50th or the 57th index. Okay, so when I do the normalization, I have to divide by 50. Okay, which is the number of points that I have between the leftmost and the rightmost index. Okay, so I have to divide by 50, and I sum over all the 50 points that I have between these two splitting points, splitting indices. Okay, and this is something that we learned in the previous lecture. So given thetas, so given r's, I know how to compute the thetas. Next, and again, this is something that that we talked about before. Next, there is a problem of representing, of finding these indices, because this is an integer problem. Okay, so finding the indices themselves is difficult. So what I will try to do is consider the breakpoints as being some belong to the continuum R. So this would be my R, and my points would be instead of just selecting my splits as indices, I will try to relate to a value. In order to do so, let us define a probability. Now, this probability is a strange probability. Why? Because it would get really, really high values where I have my numbers. So if I have n numbers, then this probability should get a value of infinity at these numbers. Okay, I denote it as errors just to tell you that if you go, if I would have had a larger screen, at the end of the day, it would go to infinity. But this probability also have, it is denoted, each of these guys is denoted as delta of x minus x1, xi, okay? Now this function delta, this is the delta of Dirac, has the following interesting property. If I integrate over this function at just this small interval, then integrating over this infinite values, what I would get, surprise, surprise, is 1. Let's do something which mathematicians really, really hate, and this is define this function in some intuitive, discrete way. So how would I define it? I would do it as follows. I will take my axis, so this would be my x-axis, and I would like to define my function, and this would be my y-axis, or my function, this would be delta of x, okay? And let's denote delta of epsilon, and in a moment you will understand why. And now what I would do is define my function delta to be the limit of the following function. So the width here of this function would be epsilon, so it would be between epsilon divided by 2 and minus epsilon divided by 2. And the height here would also be epsilon. Now, my delta function could be defined, sorry, so it would not be delta, my delta of x would be defined there as the limit of taking epsilon to 0 to the limit of delta epsilon of x. Now, the nice thing, yeah, any question?
Should the height not be 1 over epsilon so that it continues
You're
to
right. Who was that?
then?
So Dan said that it would be 1 over epsilon. So I remember that I'm checking your participation. So Dan is absolutely right. This should be 1 over epsilon. Why? So that the area here would not be epsilon squared, but rather 1 over epsilon times epsilon, which is equal to 1. Thank you, Dan. I was joking, obviously, I was making a mistake. So if I define my function as such, then obviously integrating over my function between minus epsilon to plus epsilon or minus infinity to plus infinity would always be equal to 1. Okay. How do I shift my function? Shifting the function is writing not delta of x, but delta of x minus the shift that I would like to introduce. So for example, xi. Okay, so now my function, instead of being centered about 0, would be centered about x of I. Okay, so this would be my function. So with this function, what I can do is define the following probability. I have my x's distributed on the straight line. And what I would like to do is define a function that would assign 1 over n to each and every of these numbers. Okay. So each and every of these numbers should have the same probability of 1 over n. So what I do is I multiply my delta function by 1 over n, and this is how I can go back to the continuum and have a continuous probability function that attains something which is different than 0, in fact infinity, only at the points where x is equal to xi. And the probability is defined in a weak sense. I mean, in order to define the probability, what you need to do is integrate from x to x plus delta x, and this integration gives you the probability at the point. Okay, so this is how the probability function is defined, and when we'll use it, we'll integrate it between p of x and x plus dx. Okay, so let's see where it leads. So I can obviously compute the expectation. The expectation would be nothing but, this is the definition of the expectation. This is the definition of the expectation. It would be x times px, and I integrate over minus infinity to plus infinity. So immediately I can write it as sum of all my xi's times 1 over n, because integration over my when x is equal to xi would be 1 over n, and this would be obviously the average of all my numbers. Okay, so the expectation with respect to this strange and continuous function would be nothing but the average of the numbers. Okay, next what we'll do is we'll define a way to represent the random variables x of w by my k representative values between theta 1 and theta k. And select a threshold and define a mapping which is called quantization function, which maps R into the set of values that I have. What do I mean by that? What I mean by that is that I'm building the following function. So this would be Q of, sorry, this would be Q quantized of x. So this would be my x value, and assume that somebody is giving me the R, so this would be R1, R2, etc., etc. What I'm saying is that Q of x maps all the numbers between 0 and the first index at which I'm jumping. All of these would be equal to theta 1. Then I have a jump, and all of these numbers would be equal to theta 2, etc., etc. Obviously, this would be a piecewise constant non-decreasing function. In fact, increasing function if I don't look at this constant. I mean, it would be non-decreasing along these intervals and increasing if I'm looking at the intervals as sparse events, okay? So between 0 and R1, all the x's are mapped into phi 1. Between Ri minus 1 and Ri, what I'm getting is the representative of theta xi. And between the last splitter and the end of the interval, all of the values would be mapped into phi k, okay? And this is a function of k levels, and each and every level, in fact, represent my thetas, okay? So Q, it's remember it as a quantization function, and Q is also written in a similar way to theta, so remember that Q attains only the theta values, okay? So this would be my quantization function. At the end of the game, I mean, I'm now, this is the artillery that I'm using in order to tear you up. At the end of the day, what we will see is there is no remedy, there is no refuah, but rather to do a very ugly and awful wonderful idea. And this is splitting the problem into two separate problems, optimizing for thetas and optimizing for R's. And this is in fact a classical way of solving problems in the quantization arena, but let's wait with it a little bit. So what we did is we restate the problem of representing my n values as one of representing a random variable with k values. So k is obviously smaller than my capital N. And we do it optimally by selecting my splitting values and my representative values, okay? So now, since I've been able to write my problem as one of using a continuous function with a delta function, my p of x, so I can write it in a continuous fashion. Why? Because it would be easier to optimize a continuous function. And in fact, since I have only k levels, piecewise levels, I can write it as summing over the k intervals of constant phi i's, okay? And this would be my optimization function. And obviously the split R0 sits at minus infinity, and my k, remember that I have between 0 and k minus 1, so my k would be plus infinity. These are the endpoints of the range of my axes. So what I have is I have continuous values and continuous for the representative and continuous values for the splittings, and this is what I would like to optimize for. And the question is, how do I do that? Okay, so we said before that if we fix the splitting points, then the optimal values would be nothing but the averages. This is something that we have seen before. And it would also be true for the continuum. So remember, what we have here is the range of x's that are falling in this interval, and I have to define each and every point by 1 over n. But the probability of choosing every one of these points would be 1 over n times the point itself. So I have this 1 over n here, and I have this division by 1 over n, so these two would go out. So what I would have is nothing but the average of all the points sitting in an interval. So if somebody is giving me Ri minus 1 and Ri, my optimal representation of all points sitting in this interval would be nothing but the average of all these points, okay? So it would probably be somewhere here. Okay, next. So there is also this important observation. So if somebody is giving me these values, and this is what Sean was saying, and we have the values of x that belongs to my R as realization of this theta, then x must be assigned to the closest representation value. So again, somebody is giving me my theta, so this would be my theta 1, and this would be my theta 2, and here would be my theta 3. So if somebody is now giving me a value somewhere here, the assignment would be to the theta which is closest. Okay, and this, by the way, holds not only for R, not only for scalar cases, but for any Euclidean space that you can think of, or to that matter, to any metric space that you can think of. Okay, so here should be RD. Okay, so it would not hold only for R1, it would hold also for R2, for R3, etc., etc. By the way, just a question. Assume that I have my thetas, so somebody is giving me my thetas. And now I have to split and assume that these thetas are in R2. So this would be X and this would be Y. And somebody now is telling me, look, split your domain so that each point in the domain, so now I'm choosing an XY. So this would be an XY. And I would like to know, according to the coordinates, the XY coordinates of this XI, I mean, X stands for the X and the Y. I would like to know to which point to affiliate it with. What would be the splitting mechanism or the splitting scheme to the plane that would allow me to really quickly affiliate each point to the nearest neighbor? I mean, how would you do that? What is the name of this splitting of the plane? Anyone knows? Anyone learned?
K-means?
Again?
K-means?
So K-means will go to K-means, but before K-means there is something else that what we'll do right now, I mean, juggling between optimizing for thetas and optimizing for R's would be called K-means or max Lloyd. But I'm asking a different question. I would like to know how to split my domain. Assume that I have only 2 points in the plane, theta 1 and theta 2. Okay, so all points that are falling at this part of the plane would belong to theta 1. And all points that are falling on this point of the plane would belong to theta 2. Okay, so this plane, this line that splits the plane into two, has a name in the more general sense of splitting the plane into K regions. How is it called, this splitting of the plane into K regions? Anyone knows?
I think Voronoi.
Polygon or polytope?
Again. Somebody said something that begins with V.
Polygon or polytope?
You said it might be Voronoi diagram. I heard about it in
So this is Igal.
Yagel, yes.
Yagel, sorry, Yagel. So Yagel said something which is called Voronoi. This is called the Voronoi diagram. And what Voronoi diagram says is the following. Take each and every 2 points and find the nearest 2 points and find the splitting mechanism between them. At the end of the day, what you get is a split of the plane into regions. And this region is called Voronoi diagram. So, and this is called a Voronoi cell. And this Voronoi cell, if this is theta 3, so this Voronoi cell belongs to theta 3. So theta 3 would be the representative of the cell 3 in this Voronoi diagram. So there is a very simple example. Assume that each and every representative is a hospital in Israel, okay? And somebody now suspects that he has a COVID, a coronavirus. Now this is Haifa and this is Tel Aviv, and you live somewhere, I don't know, here in Hadera. Where would you go? Would you go to Haifa? Would you go to Tel Aviv? So now somebody in the government did the split for you and said that Hadera is closer to Haifa. So it would tell you that you would have to go to Haifa. Why? Because the Voronoi diagram says so. Obviously, we don't account for the quality of physicians, and we don't account for the fact that in Tel Aviv you'll probably get worse or a better treatment, but this is just a matter of distance. If you'd like to weigh it, if you'd like to weigh other factors, you need to push it into the definition of your weighing function, okay? So this is called the Voronoi diagram, and it's a way to split your domain into regions which are closer to the point, to the representative points, okay? Now, in the plane, if I have n points points in the plane, and you would like to compute the Voron diagram of n points in the plane, what would be the complexity of comparing these Voronoi diagrams, again, in R2? Anyone has any idea? I mean, what would be the complexity in the worst case?
N squared.
N squared. Okay, who was that? N squared, because you have to compute the intersection between each and every 2 points, and then you need to manipulate them somehow and prune them so that only the variables count for, and assume that some wizard is doing it for you. So N squared would be let's call the straightforward solution. But now it appears that in computational geometry, there is a very nice way of solving this problem in n log n. In fact, it's one of the only algorithms that works in computational geometry. And this is using a sweep line algorithm. But you need to remember that in the plane, there is a very efficient way of finding the Voronoi diagram. In higher domains, it's a little bit more complicated. Okay? So let's go back to our game and assume that that somebody has given you the representative values. So immediately you know where to place the splitting points. Okay, these are the midpoints, the points in the middle between each and every 2 theta's. Okay, we are ready to continue. And as I promised to you, we will continue until 10:30, and then we'll take 20-minute break, and then we'll continue for another hour. So again, if we know the R's, we can determine the thetas. If we know the thetas, we can determine the R's. And in fact, what we have is we have to optimize for a problem with 2k minus 1 variables, okay? So if I, by some naive way, taking the derivative with respect to thetas, and then taking the derivative, so this would be the derivative with respect to thetas. And then I'm taking the derivative with respect to Ri's, okay? And remember from your high school calculus that if you have an integral over something, and here you have Ri, and you take the derivative with respect to Ri, then it is equal to this something, let's call it something here, x minus. So this something here would be nothing but x minus theta I, okay? And here you plug in the Ri with the minus sign. Okay, and this is where we get these guys. So again, what we get is k equations that I have to solve here, and I have k equations that I have to solve here. One of the equations is trivial, so I have again 2k minus 1 equations to solve for. And as I promised you, this is a non-trivial problem. So again, if we know the Ri's, what we get is the average. What we get is the average of the thetas. And if we have the thetas, what we get is the midpoints between the thetas. Okay. So these are necessary conditions for optimality. So if I would like my phi function with the derivative of my functions with respect to all my variables to be equal to 0, I would have to satisfy both these conditions. And finding them simultaneously, as I promised you, is a hard problem. So what do we do? So first of all, let's go and evaluate the expectation mean square error. Obviously, it would be mean square error because this is expectation. If somebody has provided me with the optimal solution, okay? So somebody has given me a solution that satisfies both these equations, this equation and that equation. Now the question is, what happens if I plug it into the optimal MSE? Okay, so remember from the previous slide, we used the fact that phi I equals to integration over pi in the Ri minus 1 to Ri interval. There should be dx here, And here I have integration over the same interval of px dx. So this is known, as well as the fact that the ri's are the intermediate points between the theta i's. So this is how the this is what I would do. I would sum over all my intervals, and within each interval, I would sum the square error and multiply it by the probability. Okay, so if I do that, I can now open the brackets and play with the summation. So what I would have here is this guy. The thetas are constant within each and every interval. So I would have, so this within each and every interval. So I can pull them out of the integration. And here I would have, I'm using, I'm just opening the brackets here. Now from here to here, what I would do is use this equation over here. I mean, I will plug in the optimal thetas. So if I plug in the optimal thetas, this one reads as it should. And instead of theta, I can write, so this would be x, there is a missing x here, okay? Instead of this guy, I can write theta, so I can square this guy here, and then instead of the normalization, I have to multiply by theta. And here I have the same term here. So from this equation over here, I'm getting this equation over here, and in fact, this guy is written here. And this is exactly what was written in the previous slide. So now I can, so this one remains as is. And here, what I would do is split my thetas into my averages within each and every interval, which would read exactly what is written here. Okay. So at the end of the day, what I'm getting is sum over the second order moment, surprise, surprise, minus squared the first order moments, okay? My thetas were the first order moment within each interval. And obviously, it should be multiplied by the probability of x belonging to this interval. Okay, what do I do with that? For now, not much, but let's see where it leads us to. So again, we are dancing about the same problem again. And as I promised you, those of you who heard about the Grinch who hate Christmas, we have an awful wonderful idea. Who knows about the Grinch who hate Christmas? Not many. Look it up. It's a very beautiful cartoon by Dr. Seuss. And when you think of a terrible idea, that gives you a solution, he calls it an awful wonderful idea. And this awful wonderful idea is something that we already know of. It's called K-means or Max-Lloyd. Or Max-Lloyd, in a moment, or Lloyd-Max if you write it mathematically. And the question is how should we optimize this terrible problem that I told you is hard to solve? So the assumption is that somebody is giving me a set of splitting points. So somebody has been giving me in the plane a set of points that define the Voronoi diagram. And what I would do is now affiliate each and every point within this Voronoi diagram to the representation level. So somebody has given me a set of decision levels. And what I would like to do is compute the corresponding optimal representations over the that are defined by my splitting values. So what I would do is now look at all the points that are falling within this representation level and represent them by the average. So this would be the average here, and assume that the average here would be this guy, and assume that the average here would be this guy. And what it would do is define a new Voronoi diagram. So now I can recompute the Voronoi diagram, the splitting values. So the splitting values in the scalar case would be nothing but the average of 2. In the two-dimensional case, it would be. So Avish, do you have any question? Avishai or Avish?
No.
Well, because there is noise from that direction. So if you can mute it, it would be nice. So what would happen right now is I could split my domain into a new Voronoi diagram that would correspond to these values, to these new values. Now, what would happen is that splitting my domain into these new values, I would look at all the points that are sitting in this new Voronoi diagram, and they would represent a new representative function, and all the points that are sitting in this new Voronoi cell would represent a new representative numbers, and the same goes for the third one. And these new representative would define a new Voronoi diagram that would be, for example, this guy. I'm deliberately exaggerating. And we iterate. So again, what we would do is look at all the points that are sitting, now I have a green number, at all the points that are sitting in this Voronoi cell, and they would choose a new representative, and all the points that are sitting in this new yellow cell would choose a new representative, etc., etc. And I would get a new Voronoi diagram. And hopefully, at the end, I would converge to a Voronoi diagram, to a representative set that would not change anymore, okay? Or would just change a little. And if this happens, I would converge and say that what happened right now is that I've found my good optimal representation set. Would this be optimal? Not necessarily. But what I can prove easily is that each and every such iteration would reduce my MSE error. So the MSE error at each and every of these coordinates-wise descent iterations, we call these the R coordinates and these the theta coordinates. So each and every iteration of optimizing either for the R coordinates or the theta coordinates would decrease my function. So the function would always decrease. But it is not necessarily a convex function. So what could happen is that you could be trapped into a local minimum. Let's draw this function as some higher dimensional space. What can happen is that, assume that this is the global minimum, what can happen is that you can be trapped into this local minimum. This awful wonderful idea is known as the K-means algorithm for obvious reasons. Why? Because what you do is you decide about the K splits and then the K representative, and you iterate them between them, and it optimizes for the means, okay, for the mean error. But you don't have to do the means. You can play with any metric that you like, and then you iterate between optimizing for the splitting mechanism and the representatives. And there is not much you can prove about it unless you assume some really restrictive assumptions about your probability function. So if you have some assumptions about your probability, then you can do something. Otherwise, for an arbitrary probability functions, there is not much you can do. Okay, so again, for each step, you select which coordinates you optimize for. And this is called coordinates-wise descent. And it is called the Lloyd-Max or Max-Lloyd algorithm, or the K-means algorithm, clustering method. It is called clustering method because at the end of the day, you have your points in some high dimensional space, and you have decided how to cluster them into a representative here on the left and a representative here on the right. I mean, this would be the right and this would be the left. Okay, so, and again, what is guaranteed is that the error at step t+1 would always be smaller or equal to the error at the step t. And when do we stop? We stop when there is no or little improvement, assuming we are at a local minimum. So remember, the K-means algorithm, the Max-Lloyd algorithm, I didn't prove to you that it converges to a global minimum, but it is easy to see that you minimize your function each and every iteration. So in the homework, what you would do is you assume that now your x is being randomly sampled between x low and x high, and uniform probability means that this would be 1 over the interval. So you can define it infinitesimally as that guy. Now, with the Max Lloyd, you would start with an arbitrary decision for the splitting values. So you just randomly sample k numbers that would split your domain, and then you iterate between thetas, between your representatives, and changing your values. So this is a one-dimensional problem. You can do it in MATLAB, or I don't know, in Python, or whatever you like, and you can see how eventually your hopefully your values, your Ri's and thetas would be distributed uniformly over the interval. Okay. And this is just what is going on. You can show that if you have chosen, if this is your initial split, then and again, the first value would be 0 and the last one would be 1. Then in the first iteration, these would be your thetas, and in the next iteration, you can explicitly write the splitting point. So there would be the average between R1 divided by 2 plus R1 divided plus 2 plus R2 divided by 2, and you can iterate it, and you can show the iteration for the Ri's. And if I'm telling you to do some analysis and tell me what would my IR converge to, I mean, what would be the convergence? What would be the finite value of my Ri's? What would you do? I mean, this is the algorithm that would take the previous Ri's and iterate them. So what would you do in order to show something about? Let me just put it in the center of the slide. So I'm telling you how this. So I have my R0, R1 until RK, or R capital N, I don't remember, or this would be RK. And I know how these R's are being processed by this matrix M. Okay, so this would be at time 0. And I know that this M is operating on this matrix, and after one iteration, it would give me R01, R02, etc., etc. And this matrix is nothing but, I mean, the structure of this matrix would be nothing but 1/4 half and 1/4 here, and this would go along the diagonal. Okay. Okay, so this is a tri-diagonal matrix. This is the matrix M. And from the iteration n to the iteration n plus 1, what I need to do is multiply again by this matrix. Okay, this is writing this operator in matrix form. Okay, so this is the capital M matrix. And does anyone has any, this is called the Toeplitz matrix. Okay, it's a very unique and special matrix. But assume that this is your matrix, and you'd like to explore, to investigate, to do a research. What would happen asymptotically to your K, not K, sorry, Rn, when n is really, really large, where n goes to infinity. So what would you do with this? I mean, how would you attack this problem? Anyone has any idea?
We would diagonalize the matrix M, and then we can easily put it to power of n or k.
So what Alexander was suggesting is to diagonalize the matrix M. So you can write the matrix M as what, please? As some U, some eigenvalues.
Yeah, it's marked, yeah.
Some eigenvalues, U transpose, something like that, okay? And now taking the power of this matrix would be equivalent to?
Taking the power of delta.
Yeah.
U delta power of n.
And so thank you, Alexander, and who else was there? Mark?
Yeah, it was Mark, actually.
Mark and Alexander, thank you. What they are saying is that in order to explore what is going on, what I need to do is take the power of this decomposition to the power of n. And in the limit, when n goes to infinity, what I need to do is just look at the highest value of this lambda and explore to which eigenvector it belongs. And surprise, surprise, this matrix has a really nice decomposition, and the first eigenvalue would probably be the constant one, and therefore it would probably divide my uniform unit into equally spaced regions. Okay, so there is a nice way of exploring this problem by just eigendecomposition of the operator that is doing the the splitting here. And if you didn't understand what I was saying right now, please go into your algebra books and explore it. Why? Because this mechanism is something that we will explore again, because this is how you do signal processing, at least in the linear sense. This is how you prove that your basis of operation is optimal in some sense. And if you go into curve domains, and when you do learning, for example, in non-linear shift invariant domains, then you would do things that are really similar to what is going on here. So deep learning, DNN in geometric domains relies heavily on decomposing operators into their eigenfunctions and eigenvalues, and then working in this eigenspace. Okay.
In this situation, because the toplets matrix is actually circulant, doesn't that make the matrices, when we diagonalize, isn't that just a Fourier matrix?
Done. Is this matrix circulant?
Yeah, it's 1/4, then 1/2, and then 1/4.
No. Let's zoom in into what is the definition of a circulant matrix. A circulant matrix is a matrix whose first line determines the matrix, and then the second one would be a circulant. So the element here would show up here. Okay,
and then it would just be shifted by 1 because it was one.
Shifted cyclically by 1. So you cycle it by 1. Now, this matrix that I'm showing you here is not a cyclic matrix, because when I'm looking at the endpoint, I'm not pushing it backwards. Okay, so it would be the first one would be 1/4. I mean, you would not, these terms would not show up here. Are you with me? So this
Yeah, I understand that they shouldn't show up, but I was seeing, and it's not an exact circulant matrix, but it's
you are right.
You are right.
It's a toplet, it's not a circulant matrix. They are related, they are closely related. And obviously what you would get is something like the harmonics. It would be the harmonics. And in fact, let's call them the harmonics. It would not be the Fourier for this specific case, but this is something that can be easily analyzed for, okay? So it would not be exactly the harmonic, but something related to the harmonics. So yes, you are right. And if you really want to look into this analysis, you can look at Freddie's paper with Wagner from 1997. And this is the way to go into analyzing these kind of matrices. And again, if you think about the harmonics, okay, so what would be the first eigenvector of the harmonics? It would be the DC, the constant, okay? It would be the one that corresponds to the smallest eigenvalue, or the largest, it depends how you define it. So it would be very easy to analyze this kind of asymptotic behavior. Okay, so what can we say? So if we have our x's uniformly distributed, the optimal decisions in the Max-Lloyd algorithm would probably converge uniformly over 0, 1. Okay, this is something that by hand waving you can prove. I mean, or go to the relevant paper and prove. So Ri would just be a split over my domain at the right place, and then the thetas would be nothing but the average of these Ri's. And the probability would be 1/k of having a point in each k interval. In this case, we can compute the expected error. I mean, we can have an equation for the expected error. It would be nothing but, instead of the probability, it would be nothing but 1/k. and I can split. I mean, it would be, where's the probability here? I can have my probability here, and here it would be again my 1 over k, and it would go into that guy, and I can work it out. In fact, there are some inaccuracies if you go to Freddy's notes, but you can try and work it out. I mean, I gave up after a while, but I'm no longer an undergraduate or a graduate student, so you can work it out if you wish. Okay. So in this specific example of a uniform distribution, you can search for the solution of my 2k minus 1 equations and 2k minus 1 unknowns, and you can solve it explicitly. And in the end of the day, what you'd get is that the Ri's are equal to that guy and the Ri's are equal to that guy. And I'm running over time, so let me stop here and let's reconvene at 11 o'clock. Okay, so let's take 20 minutes break and let's meet again at 11 o'clock. Okay. So we are 11 o'clock, yeah? Sorry for pushing it for more 20 minutes extra in the previous lecture. If I do that by mistakes, please raise your hand and tell me that you need to have your coffee in the middle between the two lectures. Okay, so what have we done in the previous lecture? Let me recap that. What we have done is we have mapped a random variable x omega with its probability into a probability function which we called q. Sorry, q. And this q was able to is represented by k constant number, phi 1 to phi k. Okay. So if this is my if I know how to probabilistically define xw, and somebody gave me q or my theta k values, then I can define the error. The error would be nothing but subtracting from xw the relevant theta of w. Okay. So what would be the error of the optimal representation? The error of the optimal representation, if we've seen before, would be nothing but subtracting from my second order moments the square of the of my x square, the square of my representative, of my optimal representative, and both of them are multiplied by the right probability at each and every interval. Okay. In the uniform case, we have seen that this would be nothing but 1 over the capital K number. And what we can write is that this is equal to nothing but the square, the second order moment minus the squared of the constant value theta that I have at each and every interval. Okay, so remember this equation. This is the definition of the error when we plug in the optimal representation for each and every interval. What can we do with that? So what we can do with that is the following. Is define the expectation of the squared error. Let's write the expectation of the square error. So if you write it, it would be nothing but, this is writing it explicitly, and from here to here, we just use the equation in the last slide and get this equation. If we take a derivative with respect, or before we take a derivative, if we write it, I mean, if you write this equation as follows, what we get is that this equation equals to that equation. So this one from the previous slide, and this is a direct write up of the error. And what we get is that this equation holds that we see over here. And in fact, what we can see is that the expectation of the error when you when you project it, okay, the expectation has a projection mechanism over the theta equals to 0. What does it mean? It means, let me just see how I can do that. It means the following. If we look at in a statistical sense, okay, so let's look at the set of all my set of random variables defined by my quantization function q. Okay, and this would be my my origin. Then and by the way, the x w is somewhere here above this place. Okay. So what I'm doing is I'm projecting, so this would be x of w, this would be my random variable. What I'm doing is I'm projecting my my x of w onto the space of quantization values, and the realization here would be theta of W, and this interval would be nothing but the error. So this one is nothing but the definition of the error. Okay, this is by definition the error. It would be x W minus theta W. And as we have seen, the projection would be orthogonal. Okay. So what we can say is that the error is orthogonal. Why? Because the dot product, the inner product, let me just go to the previous slide. The inner product between x W and the error is equal to 0. So if we bring it back on, what we see is that this vector, when we dot product it with that vector, statistically they are orthogonal to one another. So in a sense, and this should not come as a surprise. So again, what we can say, let me use a different color, is that the error is orthogonal to the quantization level in a statistical sense. Okay, and we have seen it that E of epsilon times equals to 0 from the construction of finding theta to be the optimal ones. So in the specific case that we have seen, in the uniform case, we could select our theta intelligently, and we could come up with everything that we would like to explore about this process, and everybody was really happy. The question is, how can we push it forward?
Can I ask a question?
Sure. Owen.
Does the XW have more dimensions than the theta W?
The XW, no, they have the same number. Remember that both of them were defined on X. Okay, so between, I don't know, some X low and X high. So both, if I'm looking at, let me just remove these parts.
Yeah, right. But in the like the painting, it looks like XW is like a three-dimensional vector. I'm trying to like understand the intuition.
Yeah, because if you look at the set, so the domain, the mapping would be from X to, so this is called the embedded space. So it would be part of R into some omega. So X would be the set of all functions. Okay, this would be X of W. It would be a realization of all functions, and therefore I plot it above my schematic theta space. The thetas, or the Q function, would be only the piecewise constant, not like that, the piecewise constant monotonic functions. Okay, so schematically I can look at it as lifting from the piecewise constants to all the functions, to all the monotonic, non-decreasing monotonic functions. Okay, and this is why I allowed myself to write X omega above the plane that we just talked about. Did I answer your question?
Yes.
Okay, so let's move on. Not that one, that one. Okay, so now let's do some approximations. What happens when I have a lot of representation values? So now K is really, really, really large. So now I would cheat a little bit. And what we would do is, so again, K is large, and you can almost think of it as some continuum. And then the question is, how should I distribute my Ks, my theta functions? And intuitively, it should be somehow proportional to the probability of guessing numbers on my interval. Okay, so assume that this is X low and Xi, and assume that I have higher probability of guessing numbers, of finding numbers here than finding numbers there. Then obviously I would like my thetas to be more, let's call it more dense here than here. So there should be some monotonic function relating the probability P of X and how I distribute my K values. So assume that you are about to, I don't know, design a new color screen, a new TV for your home. And you look at all possible videos that somebody is transmitting in really high resolution. You don't have any limit on the intensity levels that somebody is recording. And now you have to resort to, I don't know, to only 24 bits. Now 24 bits is a lot. So what you would like to do is see how colors are being distributed in all possible images. And you see that you see a lot of greens, but rather a small number of reds, or high greens than low greens for that case of, for that argument. So what you would probably do is you try to split your greens, your high greens into fine details and your low greens into low details. Am I correct in this observation? I would be correct if the human eye would have been sensitive in the same manner to low greens rather than high greens. You have to take this into account as well, but I will not confuse you further. So assume that somebody has given you a really large number of K and a continuous function that defines the probability, the monotonic function define the probability a probability that defines an integration of this probability would be one that defines what is the probability of guessing a number X in this domain. And now what I would like to do is find my quantization function. So let's write explicitly the error. So the error would be xi minus theta I that multiplies the probability function. And now what I will do is I will further assume that the probability function is a smooth function. Okay, and what do I mean by smooth? I would assume that if, for example, I zoom in into, so assume that these are two thetas, or these are two ri's, and I'm looking at the, so this is ri minus 1, and this would be ri, and I'm looking at the behavior of my p function, of my probability function. I could represent it quite well by picking the point in the middle, okay? So I can represent the probability by taking the probability, by looking at the probability at the middle of the interval. Okay, so the probability could be approximated as such. And this actually gives me a really powerful way of solving, of expressing the MSE error. Now again, this is cheating, okay? This is assuming that I can do that. But if I can do that, what I can now do is basically integrate over this function. I mean, I can write the integration explicitly at each and every interval. It would be nothing but x minus theta I to the power of 3 divided by 3. This is an equation that you should have learned in high school, so I would not explain it. And you can, in fact, write the error explicitly as being given here at the bottom. Actually, it should also include the 1/3. Okay, so this is an explicit equation for the error. So what can we do with that? What we should do with that, let me see if I corrected in the last lecture, this slide was wrong, and now I see that we fixed it. So in this case, we can determine the thetas and the r's as follows. We have an explicit way of writing the probabilities. So what we do is we equate, we take this equation and we take a derivative with respect to theta I and make it equal to 0. And then what we get is this equation for the thetas that we get over here. Okay. And at the end of the day, surprise, surprise, what we get is that the thetas are nothing but the average between every two ri's. So this is just the beginning of the, this is just the beginning. What we'll do is we'll plug this equation into the equation above, into this optimal equation. So now we know what are the thetas. So let's plug the optimal thetas into the definition of the error. So now we'll plug it into the definition of the error. Let's do that. So again, we plugged the optimal error, which is nothing but, so this would be nothing but the averages. So these are the optimal phi, and this would be phi plus 1 or minus 1. And then what we have is that if we work out these equations, we get the following equation. So again, now what we need to do is take a derivative with respect to Ri. Okay. So if we take a derivative with respect to Ri, before we take a derivative, let me just, so remember this equation. So it's 1 over 12. Let's do like that. Okay, so what I'm doing right now is I'm taking, I'm taking 1/3 over here and putting brackets about everything. Okay, I'm allowed to do that. Okay, and it appears that if I now treat this function and call it mu, okay, so this function now becomes u, then I can define the error to be 1 over 12. This is the normalization. This is the famous 1 over 12 that we got from here. What we can do is get the error to be sum over all these mu i's to the power of 3. Okay? Which is exactly what is written here at the bottom. Where this is the definition of the mu I. Okay, what can we do with that? Now, what can I do with that? Let me just show you that mu I has this special property that if I integrate over my mu I, so let's see what is going on here. This can be regarded, the difference between every two nearby splitting points can be regarded as the x. And this guy can be regarded as x in the middle. And what I do here is I integrate over my probability to the power of 1 over 3rd. Okay, now since the probability is a given function, integrating over the probability is a constant. In fact, if I wouldn't have 1 over 3 here, what I would get here is 1. But since I have 1 over 3 here, this is the square root of px, I get another constant. And this constant is something that I can relate to. I can write it as, I don't know, I can give it some name, okay? And the name that we gave this constant is, I don't know, tilde m, just to confuse people, okay? So not mu, but rather some capital M like that. So let's do that. Yeah, questions? Okay, so let's do that. I'm defining it by some constant. So again, remember my estimated square error is mu to the power of 3, and I know that summing over my mu is equal to m. Okay, these are the two values. Now, what would I do? What I should do is optimize. So I'm optimizing over my mu i's. So assume that somebody is allowing me to somehow pick up my mu I. And remember what these mu i's have been. These mu i's have been exactly that. So if the pi is given, I can immediately define the ri's. So let's optimize for the mu i's such that the sum over mu i's is equal to m. And for that, we resort to Lagrange multipliers. Okay, so we add the constraint times a Lagrange multiplier. And what we do is we take a derivative with respect to mu I that is giving me, sorry. So we take a derivative with respect to mu I that is giving me this equation. Okay, so this is how mu I is related to the multiplication to the Lagrange multiplier. And what do I need to do in order to solve that? If we resort to the Lagrange multipliers, what we can do is we can now plug in instead of lambda the constraint equation. So we take the constraint equation and we take the result that I would have gotten from the Lagrange equation, Lagrange equation. So I'm getting this equation, and this is the constraint. And now what happens is that I'm getting as a solution that I mean, from this guy, I'm getting that guy, and therefore the optimals phi i's would be nothing but sum over my mu over my p to the power of 1/3, as far as I remember. Okay, times, I mean, this would be, sorry, this would be m is nothing but the integration of p 1/3 dx. Okay, so this is the m, and I'm getting the mu I, the optimal mu I, is to be a constant which is equal to nothing but m divided by k. So again, k is my largest number, and I know exactly how each mu I should look like. So what do I know? I know that my mu I equals to nothing but the sum over the probability divided by k. This is the constant, the m constant that I'm looking for. What can I do with that? So what I can do with that is define a function. Let's define a function that somehow looks at let's define a function with a function of this x, okay, that observes this function and can split it between integration between xl and some value. Let's take this value to be some continuous value along the x-axis, and let's call it r. Okay, if we do that, I mean, let's define it. Let's call this function delta of r, which is nothing but integration. Just one second. Let me ask my guys to be a little bit more quiet. Guys, believe me, after the corona, when they lift the curfew and we can talk at class, this would also happen, but not with not with members of your family. So what happens now? I've defined this function, and this function, since I've defined it over the whole interval, I can obviously define it at the points where I want to do my splits. Okay, so this is the definition of the function where I want to do my splits. And since I know that this function is divided by, and I can write explicitly this function, it would be nothing but I divided by k, and here I have my m value, okay? And this would be my mu I. So in fact, I can write my delta functions at for each and every ri to look as follows. And obviously, if this was right for ri, it would be right for ri minus 1. I mean, all we have to do is change the ri minus 1. And therefore, I can write the delta ri to be equal to this guy, which was defined, which we have defined here. Okay, so what can we do with that? What we can do with that is define a function that tells me how to translate my uniform values my values between xl and x high. I mean, how to split my values. And these values would be, so let me just try to do something. How do I get a blank region? Let me do something like that. Let's see if it works. Okay, now I have some space to work in. So this was my x low and this was my x high. Okay, this was my x, and I had a probability function, but my probability function was translated into another function which we called, this was called R. Okay, sorry, so this is not x, but rather let's call it R. So let's call this guy R. And I had the function delta of R. And delta of R got some initial value 0 and some high value that we call the capital M. I mean, if I integrate over my whole probability between x low and x high, what we got at the end of the day is my this weird M. And what and again, remember that this guy was nothing but integration over p to the power of 1/3 of x dx running from x low to some R value. Okay, this was my value. And what we realized is that in order to have an optimal distribution, what we need to do is split this region uniformly. So if I have 7 intervals, I would have several intervals here. Okay, and now what happens is that this function is basically relating my, so this was 0 here. And this function mu, if I plot it properly, is this monotone function. Let me write it, let me do it a little bit differently. Let me do it like that, so that it would not look trivial. Okay, so this is my delta R function. Now, how do I split my x low and xh so that it would be optimal with respect to the uniform splitting of my delta function? The split is quite obvious. I mean, what we need to do right now is just go over this function and see where it lands in the x domain. Okay, so it would be dense at the beginning, probably because the probability of choosing numbers at the left part of my axis is high. And then as we move forward, it will be sparser and sparser. And at the end, it would be really sparse. And obviously, this function, this delta function, is a function of the probability. So again, it can look like that. Let me choose a different color. It could probably look like that. It should always be a monotone, different color. It should always be a monotone function, but it could have weird ways, and then the R's would be different. And obviously, once we set up the R's, the thetas should be different. So what we did is somehow, let me see if I can, come on. Let's hope it would work. And I will have to suffer from this dx until the end of the lecture. Let's see if I can remove it. No, why should I? Another way of looking at it, no. So what I will do right now, remember 60, what I will do is stop sharing and reshare, and I will never zoom in and zoom out again. Just a second. I'm reopening the the PDF. Thank you, Adobe, for being so non-user friendly. And where have we been? This is more or less
60.
it. No? Again, 60?
Yeah, you said 60.
Yeah, I don't know why it opened the text again, but this is something that I think I can get rid of. Okay. Okay. So remember what we are after. We have this delta R, which is a continuous function, and with this, by approximating this continuous function and splitting it along the y-axis, what we have been able to accomplish is in fact a quantization of my x domain. So what we would have had here is in fact this. Let me just see if I can do it again. Oh, now I'm sharing the whole. Try it again. Okay, this is better. So again, what we did here is we had our delta function, delta of R, and here we have our R, which is the something that I have to split between x low and x high. And my delta R function was a monotonic increasing function that is integration over the probability that by uniformly splitting its y-axis, I can get the non-uniform splits of the x-axis, okay? So again, this works only when k is really large. And therefore I can approximate my probability at each and every point as being equal to the average of the probability between the endpoints. If I can do that, then I can do this magic trick that I have now showed you. Now, what is an approximately, or what do we say when we refer to approximately optimal quantizer? Remember, the Q function that we had is this approximate optimal quantizer. Is what we have here is X, which is a realization of my random, choosing the random variable. Knowing the probability, I can compute delta. From delta, I mean, from the, this one was, this delta function maps x low to 0. So this was delta of x low, and this would have been delta of xi. Okay, and then what I do is I uniformly quantize my delta function, and thereby I get the k-level approximation, the quantization approximation of my domain. So this one would give me the quantization, the RIs of my domains, and obviously the RIs should not be uniform. Then I'm picking the optimal theta. That would be obviously between every two R's, it would be the guy in the middle. Okay, so this would be theta 1 probably, or theta 2. So this is how I was able to take the assumption of k large and smooth P in order to get this approximation of optimal quantizer. And now I can plug it into the into my equation, and what I get at the end is that I get the optimization, the optimal estimated square error would be nothing but 1/12 divided at times the sum over all my mu i's. Each mu I is nothing but m divided by k. Okay, and putting things, and now k can 1k can be cancelled with a 2 here, and what I have at the end of the day is that I get this number as my error. And now the obvious question should come to mind. What would happen if now, so let's zoom in into two values. I have R1 here and R2 there. Okay, and I have my theta 1 here and my assumed theta 2 there, which is exactly the midpoint. But remember that we mentioned that R2 needs to be exactly between theta 1 and theta 2. Okay, otherwise I'm penalizing a value. Assume that R2 is here, but it should be there. So this guy in the middle is actually penalized by some extra penalty. So the question is, what can we do in order to do that? We can run a little bit of Max-Lloyd in order to refine the distribution of points, but we don't need to do that because this is a second order approximation of what is going on. Okay, and again, remember that I'm always treating my probability function as some constant function, so I need to do, it's not just a matter of, so I need to do it carefully. Okay, so I'm done with this part. So again, if we suppose that the number of quantization level is high and the range of random is given here, and we have P over the range, and then we assume that we split the range into K intervals. These are uniform intervals. Uniform intervals. Then the question that comes in mind is, why shouldn't the uniform intervals be better than the whole process that I've shown you now? Okay, so the question that I can answer is the following. Assume that I don't want to go so into this very complicated scenario when I have to estimate my delta R function and then quantize it uniformly and then project it through some nonlinear function into my R, but just look at my X low to X high and uniformly sample them. Which one do you think would give me a better estimation, a better error on average? Any ideas? So again, I have the following question. We now work really, really hard to show that in order to split X low to X high properly, when I have a lot of quantization levels, what I need to do is find some strange monotonic function, split the y-axis of this monotonic function uniformly, project it onto the x-axis, and then this would be my splitting of the x-axis. Okay. Now I'm suggesting a different alternative. I'm telling you, don't work so hard. Just take the x-axis and split it uniformly. Okay, so I have two strategies. One of them is go to the complicated domain and the other one is straightforward. Which one would give me a smaller error? Which one do you think?
The intuition says the first one.
The intuition says the first one. The first one, which means the green one, yeah?
Yes. As you said before, we want to have a better representation to dense areas. Yeah.
So Gal is saying that, look, if let me just interpret in my words what I think you meant. Gal is saying the following. If it would have been so simple to split my x-axis uniformly and get better results than all the exercise that we have now done, then why bother? I mean, the intuition says that the uniform distribution should not, of these quantization levels should be worse than the green ones. But I have to prove it, okay? And in order to prove it, I need to do some, and obviously this is how you deal with these kind of problems. You need to prove. So how should we prove? So let's go into, so what would be the optimal, so this is the uniform, so this is the uniform distribution of assume that I'm now using a uniform distribution. So for uniform distribution, I can plug in the quantization level directly. And if I do that, what I get is that the optimal thetas would be nothing but the average between dividing the whole interval by k and adding half. Okay, this is straight forward. U comes from uniform uniform distribution of the quantization levels. Okay, so if we plug these uniform distributions into the error, what we would get is something that should be written in the next slide. Is again, I'm approximating the probability by choosing the midpoints of each and every interval, and then I can plug in the distribution levels, and if I put everything in the right place, what I get is that this would be the total error. Okay, so I have this total error in the case of choosing uniform distribution, and I had this error in the previous case where I chose U to be the one with the mu. Okay, so this one was with the mu or the m. And the question is, which one is smaller? Obviously, what Gal told us is that I would expect this guy to be larger, or at least larger. And the question is, how do I prove it? How do I prove that this number is larger than that number? Any ideas? Usually I have at least one student in class that knows how to prove it.
The p is always less than 1.
This is true. P is always smaller than 1, sure. Well, it's not trivial. I was joking. Nobody ever gave me the answer. I would have known it myself. But let's do the math and see. And in fact, in the end, I'm also relating to a paper that would allow you to go over the details. But for that, what we do is we resort to something which is called the Holder inequality. Okay. Let me write the Holder inequality in a more, and it relates to how we can compute the measures of some quantity. So the Holder inequality is basically telling us that the inner product, let me write it formally, the inner product between two functions, f and g, for example, in a one norm, is less or equal to the norm of f, the p norm of f, times the q norm of g, where 1 over f, sorry, when 1 over p plus 1 over q equals to 1. Yep. This is Holder's inequality. Now, in our specific case, let me write the Holder inequality for our specific case. And it uses an inequality of somebody named Young's inequality. In our specific case, what we will do is use this. In fact, it's written here. Okay. In our specific case, what we will do is use p and q to be 3 and 1 over 3. I mean, you can see this is the equation that we'd like to prove. And then the question is how to use the Holder inequality to prove this equation. Okay. So this is the Holder inequality. This is the inequality that we would like to prove. And the question is how to use this guy in order to prove this guy. Now here, I think that you could do it. If I would give you 10 minutes, at least one of you would be able to do that. But let me let's do it together. Let's define f to be nothing but p to the power of 1 over 3. Okay, this would be f, and g would be the trivial function 1. Okay, So if we make this decision, I mean, obviously 1 of x, it would be a constant number for each and every value. So if we use these selections, then obviously what we would get, let's go down. So if we do that, then what we have is that this equation, okay, we have p to the one third of the 1/3 power of p, the cubic root of p times 1. So 1 can be written as follows. It doesn't matter which metric we are using. In this specific case, we are taking the 2 divided by 3 metric. I mean, this would be the metric. Okay, so my q metric would be nothing but 2 divided by 3. And my my metric here, my p metric, would be defined as so p, and p is defined by 3. And obviously, if we take 1 over p plus 1 over q, so this is q, so 1 over p plus 1 over q, I will have 1/3 plus, and here this needs to be upside down. It should be 2/3. It should be, sorry, it should be 3 divided by 2, so plus 2 divided by 3, it should be equal to 1. Okay, so if I'm taking these two functions and I'm summing over them, then what happens is that I'm getting this equality. Remember, what is integration over p? Integration over p of x is equal to 1. Okay, this is something that we know. Now, what is written over here? This is nothing but integration over the, this is nothing but integration over the interval. Okay, so integration over the interval. So it would be integration, sorry. It would be integration over xl times xh dx. Did I mess things up here a little bit? So at the end of the day, this is what I'm getting, okay? So yeah, it should be 1 over p, and this is what I would be getting at the end of the day. So what happens is that at the end of the day, what I would be getting is this equation, is integration over something which is smaller than 1 to the power of 3 should be smaller than squared over the interval, okay? And this is indeed what I was looking for to begin with, okay? So using Holder inequality, what I was able to prove is that my mu, or my delta R way of quantizing the information, gave me better results than uniform, than using Q uniform over my data. Let's see, how much do we still have here? Not much. So now equality happens only if I have two real numbers, alpha and beta, such that alpha is equal to g and beta is equal to this guy. And at the end of the day, if I have integration over xl minus x, xh minus xl times px equal 1 almost everywhere, then I would get a uniform distribution, which basically tells me that my distribution is uniform. So I'm getting equality in the previous equation. So this equation would have equality only if p x is uniform. So equation is being realized only if p of x is uniform. Questions about this part? Any question whatsoever? If you don't have any, then please go over the lecture again. And I think that we are ready to depart and meet next week. Again,
I have a question.
Yeah, sure.
In most of the time, does it worth it and not use the trivial solution of a uniform quantizer?
Quantization. Definitely yes. Remember, just do the math. Look at how much color TV costs you. Now, this is a calculation that you have to do only once. The probability of how colors are being distributed in an image is something which I may assume is fixed. So compute it once. Now, in your TV, you usually have cinema display mode, sport display mode, I don't know, slow motion videos and whatever. If you look at them, what they do is they redistribute the M functions, the probability from scratch, and actually redo the quantization for you for each and every scenario. So again, this is something that you do a priori. So if you do the probability of values, then do it once, and then your instrument would have at least statistically optimal way of looking at the data from a quantization, from a least square quantization point of view. If your probability is something that is changing over time, then you need to think whether to do it or not. But again, as engineers, we always look for the optimality. So yes, from P, just compute your mu function. Just distribute this mu function. It should be mu of r. Your mu function of r, and then just quantize it uniformly, and immediately you get the quantization level. Otherwise, I mean, if you don't know what to do, then just use the uniform distribution. Again, we had two really restrictive assumptions. We have large K and smooth P. Okay, if P is crazy, then you need to think otherwise. If K is not large, then you need to think otherwise as well. I mean, probably K means should lead to better representation space. More questions?
So what we learned today is one way to calculate the Voronoi diagram.
No, what we learned today, thank you for bringing this up. What we learned today, so in the previous lecture, what we did is we had a set of numbers, and for this set of numbers, we introduced a single number to represent them. And we talked about the least squares and about the median, MAD. What we did today is we added numbers to the game. So we had not only a single number representative, but a couple of them, okay? And when we have a couple of numbers, we call it quantization, okay? And we did everything in the one-dimensional case. Everything was done in the one-dimensional case. In the two-dimensional case, and in the one-dimensional case, at the end of the day, we learned how to do the diagram, the Voronoi diagram, but the Voronoi diagram in the one-dimensional case is trivial in the sense that these are just the splitting points, the R splitting points. My claim was that if you use the k-means algorithm, it would apply to any dimension. So the k-means algorithm was this iterative algorithm of jumping between optimizing for the R's and optimizing for the thetas, and it would work for any dimension, but it would get you into a local minima. A local minima. It's a great algorithm. You would use it no matter what I mean, the first thing that you would ever try when you try to cluster objects is k-means. Why? Because it is simple. It's a one-line code in MATLAB. It's trivial. And it would, in some cases, in some favorable cases, it would also give you the global optimum. But it cannot be guaranteed. However, in the other case, where you have either a large number of k levels, and as well as smooth p values, p of x values, then you can do this magic that we worked so hard to talk about in this lecture. And these discussions actually led us to this crazy way of defining this integration over p and defining the splitting values and the representative values in some more, let's call it, sophisticated manner. So again, we started from points, on the line and representative numbers, a representative number. Then we added more numbers and we called it quantization. And in the next lecture, what we'll start doing is looking at smooth functions and start making things a little bit more complicated than until now.
So what we learned today is working only on the one dimension?
Yeah.
Okay.
And I'm telling you that the k-means would work in any dimension. So we learned the algorithm to work in 1D on R, but I'm telling you that k-means would work in any dimension. Voronoi diagrams would work in 1 dimension, and in 2 dimensions it's quite, and in fact you don't have to compute the Voronoi diagrams explicitly if you're using k-means algorithm, but then it would be, let's call it, not so efficient to compute the k-means algorithm. The k-mean algorithm is trivial as an algorithm, but the complexity of redistributing the points can be painful. It is trivial in 1D, it is n log n in 2D, and it becomes painful when you go to higher dimensions. And for that, what you do is you're looking for the k nearest neighbors, and you have these shortcuts of implementing the k-means algorithm in an efficient manner. Okay? But I didn't give you any hints on how to do that. I'm just telling you that it can be done using some approximation algorithms in high dimensions as well. And it is a very efficient algorithm. I mean, you can do that in a very efficient manner. Michael, more questions?
Well, thank you.
Okay, so have a nice week. Be safe, be healthy. Don't infect your neighbors. And let's meet next week.
Can I have just one general question about the course?
Yeah, Owen.
Are we gonna have like real image processing, maybe like in homework, like taking images and I don't know?
Definitely yes. Thomas, are you on? Definitely yes. You will work a lot. Again, in this course, you will work with the 2-dimensional images, I of x, y. And these 2-dimensional images, you will have to quantize them. You'll have to, you probably would also work with a set of images. This is something that we have done once. So the answer is definitely yes. But before we go into more than one dimension, we need to understand, well, what is going on in 1 dimension. Okay,
great. Thank you.
By the way, everything that will, as I told you, if we are talking about, surprisingly, if you go to advanced compression algorithms for compressing images, you'd see that they're using wavelets. I mean, this is, for example, MPEG 2000. But wavelets is something that you can prove optimality only for 1-dimensional signals. So they took the motivation for 1-dimensional signals and applied it to 2-dimensional signals. In fact, the usual MPEG that you're using probably most of the time in your compression and decompression algorithms are using something which is not really related to wavelets, but something else. And again, the same questions of optimality are coming into play. And the JPEG images that everybody, compression, the JPEG that everybody is using is in fact using cosine transform, which is not far away from diagonalizing the tri-diagonal or toplets or circulant matrices that we will learn in this course. So you would really understand where the JPEG construction is coming from, at least as long as we don't take the entropy coding into the game. So from a representation point of view, you will, at least at the end of this course, you will understand how to do a new JPEG algorithm if you have new images with new statistics, or new MPEG algorithms if you have new videos with new statistics. So the answer is definitely yes. And something else that I have to comment about, assume that you're taking all the values of your pixels in the image, and you now create a histogram. So this would be white and this would be black. This histogram is 1-dimensional, at least for the gray level images. So everything we have done until now applies to images. I mean, take an image and instead of representing it with 24 bits, each and every pixel, now say that somebody is telling you to represent it by only 4 bits. So you have only 16 levels of color to represent your image. How would you do that? Again, treating the image as treating the histogram of the image I mean, here for each and every value, you count how many pixels of the same value you have, and assume that you normalize by the total number of pixels that you have. You have created a distribution function for the image. So the one-dimensional case is really, really important when dealing with images, with two-dimensional images, with high-dimensional images. Without understanding the one-dimensional case, you will not be able, I mean, without knowing the steps, you will not be able to dance. So yes, my goal in this course is for you to be able to work with two-dimensional images, but for that we'll learn the basics.
Is there a textbook of the course?
Yeah.
Is there a textbook?
So there is, what we'll do is we'll give you, so this is a question that I've been asked several times. The answer is that the course itself is sitting between signal processing, and there what you'd care about is aliasing and designing filters and image representation or signal representation. So the answer is that no, we don't have a single book for everything that we will do here. There are many books that are scattered. What we will do is give you a copy of the slides. I'm correcting them after each and every lecture. So the printed slides should be much more cleaner than the handwritten ones by Freddie. So you're welcome to go over that. And occasionally we'll also refer you to papers. And I think that in this specific case, we also gave a link to a paper that relates to what we proved in this specific lecture. So again, use the lecture notes, use the papers that I'm using. I was teaching Introduction to Signal Processing, MAVLAS, and I was teaching image processing, and I was teaching geometry processing. And I can tell you that the way this course is constructed, and I was teaching it at Stanford, and I gave some lectures at MIT, and I can tell you that the way that this course is structured is, in my point, the best. And I'm not saying it because I invented it. I didn't. I took the lecture notes from Freddie Brookstein. I'm telling you that because the way of hammering over the issue of aliasing so much time and Laplace transform and many things that are non-intuitive, rather than attacking the whole notion of transformation from an operator point of view, is really taking away the whole essence of what you're doing at the end of the day. I think this course is structured in probably the best possible way that you can think of. So again, I'm not giving praise to myself, but rather to Freddie. And I think this is the way to go. But again, if you have any comments about material that you prefer or other material, then be my guest. By the way, at the end of the course, we'll get to something which is called the Wiener filter. And in my point of view, this is the optimal linear filter when you have statistics about the image or the signal and the noise. Okay, so you know the statistics of the noise, you know the statistics of your signal, and this is the best possible way to define a filter that will take away the noise from the image. This is classics, okay? I don't think it is so important to go over this material. In my point of view, it's much more important to go into other domains like functional maps and something which is called the optimality of the Fourier, that would tell you immediately how to treat signals which are not simple images, but rather images painted on some curved domains. So it would enable you to acquire tools that would allow you to fly from the flat, linear, uniform domain where convolution is well defined into other domains. But again, this is something that we will learn in the more advanced lecture in this course. But bear with me, at the beginning of the course, it would be simple and it would become more challenging as we go. More questions? Okay, so again, thank you, and we'll meet again next week.
Thank you.
Thank you.
Thank you.